Okay, so this is I'm going to talk about basic graph algorithms. This is again pretty important part of algorithms. Sometimes these are covered in data structures course or maybe even discrete math. So I'm just going to give you a review of some of the basic graph algorithms, okay, because the whole course is about a quick refresher on algorithms anyway. So first thing, what is a graph? You know, everybody would draw a picture and say it's a graph. Well, formally it is a set of vertices and a set of edges. So V is a finite set, some finite set, and E is contained in V cross V. Okay, it's a set of pairs of vertices. That's what a graph is. Okay, very fundamental object in combinatorics and algorithms, and graphs are ubiquitous. It appears various places, networks, social networks, electrical networks. So it's a collection of nodes and edges. An edge is a pair of vertices. Now this pair may be oriented. It may be which means that ordered pair A comma B may be different from B comma A, because that means that there is a direction in the edge. It's a directed graph. Okay, so graphs appear at multiple places, and how do you represent a graph is something very fundamental. Two popular ways of representing a graph: adjacency matrix. So it's basically will store Aij equal to 1 if the pair ij is in the edge and 0 otherwise. And another is called adjacency list. It's an array A1 to n where Ai is a list of vertices adjacent to I. Okay, each has its pros and cons. You should, anytime I give you more than one way of representing, you should ask the question, okay, what is the advantage of one over the other? What is one good for and what is the other good for, kind of questions you should ask. So, let's do a small example. If this is my graph, my vertex set is 1, 2, 3, 4, edge set is 1, 2, 1, 3, 3, 4, 2, 4. Okay. So my adjacency matrix, do at least do some examples. It's important. Will look like this: 1, 2, 3, 4, 1, 2, 3, 4. Typically, for most of the graphs we look at, they don't have self loops. So diagonal entry will be 0, 1, 2 will be 1, 1, 3 will be 1, 2, 1 is 1, 2, 3 is 0, 2, 4 is 1, 3, 1 is 1, 3, 2 is 0, and 3, 4 is 1, and 4, 1 is 0, 4, 2 is 1, 4, 3 is 1. So this is also a symmetric matrix if your graph is undirected, because whenever ij is 1, the ji is also 1. This is adjacency matrix. And adjacency list will simply say, so it's important to do some example, understand adjacency list will look like 1, 2, 3, 4, and 1 will have 2 and 3. 2 will have 1 and 4, 3 will have 1 and 4, and maybe some nil pointer. 4 will have 2 and 3. That's how this list will look like. So you should now, good exercise. What operations are easy in what does easy mean, right? Adjacency matrix, and then in adjacency list. I mean, why do I need two representation, right? You should ask this question. So this, for example, it takes n square bits because it's n by n matrix, there are n square, so in terms of space, whereas here it will be n entries and each entry will have as many cells as the degree of that vertex is. Okay, if it's adjacent to 5 guys, then it will be a list of size 5. So, roughly it's summation di, I would say log n bits, because to represent a number you need log n bits. So this is like an m log n bits. If m is the number of edges, so if my graph G, almost my notation, number of vertices is n, number of edges is m. So for example, I'll give you two problems. Is I comma j an edge? Find out how much time it takes in adjacency matrix, how much time in adjacency list to find all neighbors of I. Right? How much time to answer these questions in adjacency matrix, in adjacency list. Okay, exercise, think about it, because this, again you have to do this in class and talk about it, because it tells you when to use adjacency matrix, when to use adjacency list. One is the space constraint. I have already said one takes n square bits if n is the number of vertices, the other one takes m log n bits if m is the number of edges. So the number of edges is really small, adjacency list is actually better in terms of space, but depends on what you are doing in the graph, the time actually may vary depending on whether you use adjacency matrix or adjacency list. Okay. Now, the kind of questions we'll be interested in a graph, algorithmic questions, is, is the graph connected? What is a connected graph? Before you ask this, you should have a very well defined concept, the good definition for the problem, because if I am going to write a program, algorithm and a program to answer this question, I better be very clear about what the definition is, right? What does it mean by is the graph connected? That there exists a path between every pair of vertices. Not an edge, but a path. Okay, what is a path? It's a sequence of vertices and edges where these edges are incident on these, they alternate, edges are incident on these alternate vertices, and The first vertex, if you want to talk about a path between x and y, the first vertex is x, last vertex is y in this path. Find the shortest path. If it's a shortest path, then an edge is the shortest path. But from a source vertex, I tell you one specific vertex in the graph, and I want to know, give me the shortest path from S to every vertex. Maybe I want to find all pairs shortest paths. Maybe shortest cycle. I even ask, does the graph have a cycle? And then you may even have weighted graph, shortest paths, all pairs, single source, all that in weighted graphs. What does that mean? That suppose, for every, so it's again a graph, vertices and edges, but every edge now has a number, the distance associated with it, or maybe there is a cost associated with it, right? Shortest path in weighted graph, every edge has a number, a weight. Okay, so because a shortest path in a weighted graph, it may have like 3 edges, whereas in an unweighted graph, it may actually have 2 edges for all, but these 2 edges together, so 2 edges together may have a larger weight than the 3 edges. So they do differ between a weighted graph and unweighted graph. You can find the minimum weight spanning tree. This already I talked about in the context of greedy algorithms. So is the graph bipartite? If you don't know what the bipartite graph, maybe I will tell you about it next time. So graphs are important, I'm going to say some of the algorithmic questions we'll be interested in. Okay, so I've told you what a graph is and how to represent a graph, 2 representations. They have some things that can be done faster in one compared to the other. Please think about them. That's important when we actually design algorithms. And then there are a lot of natural algorithmic questions which we're interested in. So, okay. So, I'm sure you all will do this in your algorithms course or in the data structures course. I'll touch upon some of these, not everything, in the next lecture on, basically there are 2 graph exploration paradigms or graph search paradigm. And one is called breadth first search, and the other is depth first search. Very important and fundamentally algorithmic search paradigm on graphs. So once you are given a graph, I may just to see, remember, we have a visual understanding of how a graph will look like, but so we look at 1, 2, 3, 4 this graph here, and I can tell you that it's actually a connected graph. But if I give you this matrix, that's how it is given, or this matrix, such as a list, it's not so easy to answer the question, is the graph connected? Okay, so it requires some work, and you answer them by doing some of these basic exploration of the graph. Okay, imagine graphs are really big, social networks or some of the transportation networks can have several thousand nodes and some several thousand edges. So, it is important we have efficient algorithms for those problems. So, and many of these algorithmic questions are answered by one of the two exploratory questions, exploratory paradigms, breadth first search and depth first search. So, next time I will tell you what these breadth first search and depth first search, how they work, what are some pluses and minuses, and how they help you answer some of these questions. I may not look at all the questions, but at least tell you about it.